Okay, thanks everybody for being here. So I guess this is the bonus one because technically today, I guess, is reading day. The exam period starts tomorrow, but we'll still have another review class tomorrow, and then our exam will be on Monday, right? So tomorrow's Friday, then you'll have the weekend, right? So we did Brayton, right? We did turbojets. Today we're going to do a complicated Rankine cycle. And then next class, we're still sort of thinking about doing an internal combustion engine problem, but I still didn't have anyone volunteer to get me a problem. So if I get a problem either tomorrow or today, then I will do it. But if not, we can just have an open session where people ask questions. Because I know what's going to be on the exam, I think it's not a great idea if I pick a question because then I have to think too much about, not picking one that's on the test, and it gives too much away. So it's better if these questions come from you guys. So if somebody wants to send that to me either today or bring it in tomorrow, that's great. Otherwise, we can just kind of ask questions throughout the session. So today we are going to talk about a Rankine cycle and a complicated one. So this one is a Rankine cycle. We can see, right? We're going back and forth across the vapor dome. It's got reheat, right, in between these. There's 4 turbines here, so there's reheat in between what I would call turbine 2 and turbine 3. It's got 2 different kinds of regeneration. So it's got a closed feed water heater and an open feed water heater, right? There's a whole bunch of pumps and stuff. So I think that this is similar to the one that Dan sent me, but the one that Dan sent me, I think maybe didn't have this 4th turbine, if I was reading it correctly. But I think this one looks pretty good. The tricky thing here, and I don't know if it says that these are the same or not. These are 2 different diverted mass flow rates. So this here looks like Y prime, and this one looks like Y double prime. I don't see a Y. Right? So the first thing that I like to do with these problems is bust out some colors so I can kind of make it easy for myself to know where the mass flows are where, right? So this is the whole mass flow that goes into the first turbine. I'll use green for the whole mass flow, right? It's the whole mass flow that comes down, like that comes into this boiler through this half of the closed feed water heater. Right? But in the open feed water heater, it's different. We get, for blue, I'll use Y prime. So this is, Y prime is through here, through this half of the closed feed water. And then it comes back over here, right? So then this, going through this component, I don't know, I might run out of colors here. We'll try orange. Right? So this, that was Y there. So it's 1 minus Y through this second turbine, through the reheater, into this turbine. Right? This is 1 minus Y. And then purple, this is going to be Y prime, Y double prime, I guess, right? Well, let's just call this Y and Y prime. I think that's going to be easier for my brain. So this one here is Y. This one here is Y prime. Right, so then that means going through this last leg over here, which I need another color for. Let's do like this turquoisey kind of guy. Going through this last turbine, the condenser, and this pump over here, this is 1 minus Y prime. All right, so that's the first thing that I like to do because I feel like, and hopefully we'll see this, that this will make my life easier. It wants us to complete the state table. I'm going to do this last. As you know, my preference is to find the symbolic solutions first. Determine the thermal efficiency and the mass flow rate entering, and the mass flow rate of the steam entering the first turbine, so the total mass flow rate. So there's some things we're going to have to know. So consider the Rankine reheat regenerative cycle as shown with this information all down here. The working fluid experiences no irreversibilities. So that means that we're going to assume that the turbine efficiency is equal to the pump efficiency is equal to 1.0 or 100%. And we know the net power is equal to 12 megawatts. No heat losses, right? That's what that tells us. Okay, so first we want to find the thermal efficiency, and then we want to find the mass flow rates, right? So this basically is saying find why. It's kind of a bit of a weird way to say it. Determine the mass flow rate of the steam entering the first turbine. So that's the total mass flow rate. But I think to do that, we're probably going to have to find y and y prime and everything too, right? Okay, so first we want the thermal efficiency, right? So, you know, I guess our three big questions, right? So one, how do we characterize the system, right? So this is thermal efficiency. It's a heat engine. So we will take net power divided by heat transfer rate in. Second, is it open or closed? It is a series of open systems, right? And third, what's the fluid? The fluid is water. Or it could be something like it. It doesn't have to be water in a Rankine cycle. You could run this with something, but you're going back and forth across the vapor dome. The thing is, right, so first we're going to have to know what's the phase. And we're also going to have to know if it's an ideal pump. Because if it's an ideal pump, then delta H is equal to the specific volume times the change in pressure, right? So this is one, you know, if we look at things, you know, that are common mistakes that people make in Rankine cycles, that's one of the things that people forget is how to go through those ideal pumps. Okay, so now part A, well, part A was finish the state table. We're going to do that last. Because that's going to take me a long time to do, and I don't want to get to a point in the test where I run out of time fixing the state table, and then I, you know, so I'm sort of halfway done part A, and I didn't do part B and C, right? But I can do part B and C pretty quickly, at least the symbolic part. So this is W.net, right? So we know that our expression for W.net is going to be the sum of the turbine powers. I don't think it actually, I think it wants thermal efficiency, yeah, actually, right? So the thermal efficiency is W.net over Q.in, right? But I kind of made a mess of this whole thing, right? So now W.net is going to be equal to the sum of all the turbine powers. Those are positive, so I'm doing that in green, plus the sum of all the pump powers, which are negative. I'm going to do those in red, right? So, you know, now I got to start thinking about the first law, right? So dE by dt is equal to the sum of m dot. No, it's not. You can tell I was a little late getting in this morning. My brain's a little scattered. Q dot minus W dot plus the sum of m dot in H in plus V in squared, I think it's metric, over 2, plus GZ in minus the sum of m dot out, H out, plus V out squared over 2 plus GZ out. So what are we going to do? We're going to say all of the components, at least here in this thing. So I guess really we're not saying all the components. We're saying all of the turbines, all of the pumps, and everywhere where we're adding heat in are going to be steady state. They're all going to be one inlet, one outlet. We're going to neglect kinetic and potential energy. And then when we have turbines and pumps, they're going to be no heat transfer. And when we have, well, let's pick a different color, green. When we have boilers or reheaters or whatever you want to call them, anywhere where we're adding heat, we're going to say that's passive. So then what's going to happen is this is going to turn into the sum of m dot in, or I guess there's, of m dot of whatever the particular component is of all the turbines, H in minus H out, plus the sum of m dot whatever the particular pump is, H in minus H out. Right? So we know we have 4 different turbines and how many pumps? 2 different pumps. Right? So here we're going to, right? So this is definitely going to be more extensive than if this was just, you know, a 2-component or a 4-component Rankine cycle. Right? So this is going to be m dot of turbine 1 times, this is probably H1 minus H2. I'm going to steal this picture over here. Oh, it's coming up behind my Zoom window. Super exciting, I know. Because, and the reason I want this here, I want to be able to see what the state numbers are, but I also want to see what the mass flow rates are. Right, so the first turbine, this is going to now be, it goes from state 1 to state 2, H1 minus H2. Second turbine is m dot T2. This goes from state 2 to state 3. The third turbine, m dot T3. This is H. The third one goes from 4 to 5. And the fourth turbine, let's see if I can squeeze it in here, goes from state 5 to 6, H5 minus H6. Okay, now we're going to have plus my 2 pumps. This is going to be the same expression, but I'm adding it, right? So it's going to be a negative number. So this is m dot times H7 minus H6, or H8, I'm sorry, right? Because this first pump goes from 7 to 8, plus m dot P2 H. The second pump goes from 9 to 10. 9 minus H10. Nice, so that's good. Right, we're on the path here, but it's going to be a long one because it's a big problem, right? So again, you would never have to do this whole state table, but you could get a problem like this, and you know your first inclination might be like, oh my God, I don't know what to do, right? And that's okay, but then your second inclination's got to be, I just got to follow the process, right? I know how to get an expression for net power. I know how to get expressions for heat in, right? So we're just going to march our way through it, right? The first turbine is going to get the whole mass flow rate. I didn't draw this green line through this, but this is just going to be m dot. So m dot times H1 minus H2. The second turbine gets 1 minus y of the m dot. 1 minus y times m dot. The third turbine also gets, oh, I gotta do this, H2 minus H3. The third turbine also gets 1 minus y times m dot, plus 1 minus y, m dot. This is now H4 to H5, H4 minus H5. Right now, my fourth turbine gets 1 minus y prime. So this is going to be m dot 1 minus y prime times h5 minus h6. Okay, and now my pumps, my first pump, m dot, gets also 1 minus y prime, 1 minus y prime times h7 minus h8. And then my second pump gets the whole mass flow rate, and this is just going to be h9 minus h10. Right, the good news is we have a number for this, right? So we were told the value of this. That's good. Now get ready for the bad news, right? We don't know the total mass flow rate. That's one of the things we're supposed to find, right? So I don't know m dot. All right, that's too bad because that's in all of my terms. I don't know y. I don't know y prime. Let's see if I know any of these states. How many have they fixed for us? Oh, a fair number. 1, 2, 3, 4, 5, 9, 10, 11, and 12. So we know 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 5. We don't know 6. And then what did I say? 9, 10, 11, and 12? So that's not too bad. Not as bad as I had feared, but still not great. But the good news is we got an equation, right? We got an equation that's got a lot of unknowns in it, but we got an equation. Let's see what's going on with our denominator here, which would be Q dot in. So where are we adding heat? We add heat in over here the first time through the boiler and then the second time through the boiler. We know that this is going to be the sum of m dot times h out minus h in. So this is going to be all of the mass flow rate gets the first heating cycle, I guess, right? M dot times h out minus h in. So this is going to be h1 minus h, what is this, 11? And the second time is going to be plus 1 minus y, or m dot times 1 minus y, times h4 minus h3. Now this is good because we've got some expressions here for net power and for heat in, but the problem actually asks us for our thermal efficiency. So I can get a symbolic solution for thermal efficiency. And the good news here is that the m dots are going to drop out at least. So I'm just going to, right, because there's going to be an m dot in all of our denominators terms and all of our numerators terms. So I'm just not going to write the m dot and then cross it out because I'm going to try to conserve a little bit of space here. So this is going to be h1 minus h2. My second term is 1 minus y times h2 minus h3. My third term, 1 minus y, h4 minus h5. My next term is 1 minus y prime, h5 minus h6. Now, these are all still denominator terms. I'm just running out of space. This next one is going to be plus, I did this one. This is also 1 minus y prime, h7 minus h8, plus h9 minus h10. And all of this is going to get divided by, I'll put this all in one big square bracket to remind myself that's all one term, right? This is going to be h1 minus h11 plus 1 minus y, h4 minus h3. So we've got a symbolic solution for our thermal efficiency, but we can see there's a lot of things we don't know. A fair number of these states we don't know, and we don't know y or y prime. But at least we got a symbolic solution, right? So that's good. What was the other thing that it wanted? It wanted the mass flow rate was one of the parts, right? Thermal efficiency and the mass flow rate going through the first turbine. So the way we're going to, well, let's see. So part C is how do we find a mass flow rate? I think there's really basically only three ways we know how to find a mass flow rate. Option one is going to be area times velocity divided by specific volume. Option two is if we know some power or heat transfer term, then I can use the first law to try to find m dot. Option three is I can look for a component with more than one inlet and or more than one outlet, right? Definitely not this one. I'm going to do this first, right? Which we've already done. And this, I'm probably going to have to do this too. Right? But I'm going to start here first because the trick is in this one, they gave me the net power, right? So now I got to write this whole big long equation out again, right? So here, I'm just going to go from the net power, right? And we can factor m dot out of all of these terms. So I'm going to take m dot is equal to the net power divided by, the sum of all these terms without the m dot in them, right? So this is going to be m dot is equal to, this is also the numerator here, right? So this is going to be w dot net, which is given, divided by, let's see how long I can make this line. It's not terrible. It's not straight, but it's not terrible. h1 minus h2 plus 1 minus y, h2 minus h3 plus 1 minus y, h5 or h4 minus h5 plus 1 minus y prime, h5 minus h6 plus 1 minus y prime, h7 minus h8 plus h9 minus h10. Right, so here we knew this, right? And what was it in megawatts, maybe? Sorry, it always takes so long when I'm. This is 12 megawatts, right? So I'm going to put that into kilowatts. So here I'm going to say, this here is 12 megawatts, which is equal to 12,000 kilowatts, right? Because there's 1,000 kilowatts in every megawatt, right? So I know this. I think, what do we know? We knew H1, 2, 3, 4, and 5. And then what was the other one? 9 and 10 or something? So 1, 2, 3, 4, 5, 9, 10, 11, 12. Nine, 10, right? But we don't have those ones. And then, of course, we don't have y and we don't have y prime. So how do we do these? How do we do y and y prime? Well, we already used option 1 or option 2 here. Option 1 we can't use. We don't know the cross-sectional areas of any of these tubes or the velocities or the volumetric flow rates or anything like that, right? But we do have some components that we haven't done the first law yet for one inlet and one outlet. So for the open feed water heater and the closed feed water heater, we can still do the first law, right? dE by dt is equal to q dot minus w dot plus the sum of m dot in h in plus v in squared over 2 plus gz in minus the sum of m dot out h out plus v out squared over 2 plus gz out. Right, now for these feed water heaters, we're going to assume steady state. We're going to assume that they're adiabatic, right? It said there's no stray heat loss. That means that even though inside these heaters, heat is being transferred from some flow to some other flow, there's nothing that crosses the boundary of our heat exchanger. They're going to be passive. They're not one inlet and one outlet. That's why we picked these ones. Because the reason we look for ones with more than one inlet and more than one outlet, because those are usually heat exchangers, and those we can usually say are adiabatic. So for all of these, for both of these systems, this is going to be 0 is equal to the sum of m dot in h in minus the sum of m dot out h out. So let's see what we can do with that if I copy this and bring it down. So we can start here with, I'm going to start with the open feed water heater. I know here that 0 is equal to the sum of m dot in h in minus the sum of m dot out h out. Right, so this is going to be 0 is equal to, this is state 5 coming in. So m dot, I'm going to call this m dot 5, recognizing that it's not the mass flow rate doesn't get pinned to the state number. It gets pinned to the inlet or the outlet of the particular component, right? But I'm still going to call it m dot 5, although m dot 5, the m dot associated with mass with state 5 going through this fourth turbine is going to be different than this one. But I'm still going to call it m dot 5, h5. The other inlet is over, there's an inlet over here from the condenser. This is, I'm going to call this m dot 8, h8. There's another inlet coming here, right? So this is the stuff that goes through here, right through this trap. This is going to be plus m dot, I can't read that. Is it 13? H13, that's this state here. Right, and then we only have one outlet, m dot 9, h9. So what do? Right, we got to see what these mass flow rates are. So this first one is y prime times h5 plus m dot 8 is 1 minus y prime h8. This other one, this is going to be plus y times h13. And then we got minus the total mass flow rate, so that's just going to drop out because I'm going to divide by the total mass flow rate everywhere, right? H9. Even though I wrote down the open feed water heater first because it kind of sequentially, at least in some way of thinking, comes first here, I'm not going to try to solve this one first, right? I think we knew H5. I think we knew H9. Did we know H13? If we know H12, we also know H13 because that's going through a trap. So we do know H12, but H12 is the same as H13. Anytime you go through this kind of valve here, this is an isenthalpic valve. So this means that H13 is equal to H12. So this is also 908.79. So we know 1 to 5, and we know anything above 9. So 1 to 5 and anything above 9. So we do know 13. We don't know 8. So this one, it's not a terrible equation. I mean, it's a nice equation. All equations can be nice, right? But we don't know y. We don't know y prime, and we don't know h8. Even if I could fix the states, I can't find either y or y prime here. So I'm going to leave this one for a second and look at the closed feed water heater and see if it gives me a better equation, right? Because when I look here, and probably I should have done this first, but when I look at the open feed water heater, there's some of these states are related to y, some of them are related to y prime, some of them are related to the total mass flow rate, right? There's all the colors that are on our diagram come here at the open feed water heater. That's probably not the best one to start at, right? So at the closed feed water heater, it's still 0 is equal to the sum of m dot in h in minus the sum of m dot out h out, because it was all the same assumptions. But here, this is going to be, I'm going to look at the blue line first, right? So this is going to be m dot times y times, I'm going to go in minus out on the blue line. So this is h2 minus h12. And then on the other line, this is going to be plus, this is just m dot. And this is going to be h in is h10 minus h11. Right? We can divide the total equation by m dot because 0 over m dot is just there, right? Now we know what 1 to 5 and anything above 9 and above, right? So we know h2, 12, 10, and 11. The only thing I don't know in this equation is y, right? So here y is equal to h11 minus h10 divided by h2 minus h12. I put that up into here because now I know this. And if I could fix state 8, then I could find an expression for y prime as well. Right? Oh, it also goes in here. Right? So if then I could fix state 8, then I could come back in here, right? And start to do this stuff, right? So the next thing I got to do is fix state 8. Oh, this is, it slows down in here, right? So we can start talking about how to fix the states now, because I think that's our next thing. Now we know y, right? We like to know y prime, but at least we've got a good equation where if I can fix all the states. So really I need h6, h7, and h8, right? And then I'll be good to go. So let's get back to, oh, I guess I copied that there. Let's see what we know and what we don't know. So the ones we really want are 6, 7, and 8, I think is what we said. I'll shrink this down a bit, make it a little more friendly in Word. Right, so right, so we know we have 13. We need 6, 7, and 8. So H6 is over here. H7 is over here, and H8 is over here. So we can sort of go in order here, right? What do we know about? Do we know anything about state 6? So we know the pressure. We only know one thing about state 6. So state 6, here we know that the pressure is equal to 0.008. If this was an exam and I felt like I had no way to find state 6, then I think what I would try to do is, this is MPA, I would maybe say that it's saturated liquid, which it doesn't look like from this particular picture, right? Oh no, that's silly, right? Because obviously, right, this is good. So what we know is that from state 5, we know that from state 5 to state 6 is an isentropic process, right? So this is always the thing, right? And maybe because I was just starting in the middle, I didn't see it exactly, right? But they told us all these turbines were isentropic, right? That they're all ideal. So that means that that the specific enthalpy of states or entropy of state 6 is equal to the specific entropy of state 5. Now, state 5, they don't actually give us the enthalpy, so I'd have to look over here, state 5, right? I'm going to assume that this is a superheated vapor. And for state 5, I'd have to go to table A4, because this is water, and I interpolate to find S5. And then when I have S5, then that's equal to S6. So then when I ask myself for S6, they drew it over here under the vapor dome, but I'm not exactly sure, right? So here I'm going to say, is this two-phase or no? So then what I have to see is for here at state 6, we know the pressure instead of the temperature. For P6, what is SG, right? So is S6 less than SG, right? Because SG is right over here. So if this is a two-phase mixture, then we'll be less than SG on our TS diagram, right? My guess is this is the case. At least that's what it shows on the diagram. So here I would find S6, right? So I'd know that I'd write down my quality equation, right? So I know that X6 is equal to, well, maybe I'll write the whole thing out instead of skipping a step. S6 is equal to SF plus X6 times SG minus SF. But the thing that I want here is X6. So here I would take this equation. It's been a little while since we've done this, right? This is going to be X6 is equal to S6 minus SF divided by SG minus SF. And the reason we like that is because then we can find H6 is equal to HF plus X6. I can either write this as HFG, right? But HFG is equal to HG minus HF. But this is on the table, so I'm just going to write that down. I'm going to look this up. This is in the table. This is in the table. I use this value for S6 down into here, and now I have H6. So that's pretty good. That was one of the ones that we didn't know. So now we know H6. Now we want to find H7. So I look at the diagram. H7 is coming out of the condenser. They tell me that the quality of state 7 is 0, and they tell me the pressure of state 7 is the same as state 6. So S7, so if I'm looking at, oh, I gotta give myself some more pages here. Oh, of course they go. So for state 7, I'll do state 7 down here, and then I think I'll have to move up a page to do state 8. State 7 is a saturated liquid. P7 is equal to P6, right? So this is just going to be H7 is equal to HF at P7, right? If you wanted, if we can also get S7 is equal to SF, but I don't think we'll need it. Also at P7. Where'd it go? Here we go. So now, right, so now we've got H6, we've got H7. How do we get H8? So here's the thing. As we go, so then you got to ask yourself about the process. We're going from state 7 to state 8. This is a pump. And it's an ideal pump. So because it's an ideal pump, we know here that H8 minus H7 is equal to the specific volume of either case, but I'm going to pick 7 because I already know this, times the pressure difference, P8 minus P7. This is going to be VF at state 7, because state 7 was a saturated liquid, right? So this isn't even really a subcooled liquid approximation. It's just the right answer, right? P7 here, you got to watch your units, right? These are all in megapascals. I like to convert this to kilopascals because V7 is going to be in meters cubed per kilogram, right? So I want this in kilopascals, right? Because that's kilonewtons per meter squared. And then I've got kilonewton meters per kilogram, which is kilojoules per kilogram, right? So watch your units. That's the other thing. So people sometimes forget to use this equation. And then even if they remember to use the equation, they forget to check the units, right? And then when we went from 12 to 13, well, this was just a trap, right? So H was equal. If these were real pumps and real turbines, first you'd have to find the ideal pump exit. Then you'd have to use the pump efficiency, right? Which is the ideal pump consumes less power than the real pump. And then you'd use this. This would be H in minus H out ideal divided by H in minus H out. So you'd use this method to get H out ideal. And then you'd, or at least here, this would be V times delta P on the top. And then the only thing you wouldn't know would be H out. Right? So this problem didn't ask us for an ideal in a real pump, but we could do it, right? Just like when we went through here, when we went through this turbine, we found the ideal outlet for state 6. If it was a real outlet, we still would have found the ideal outlet. Then we would have used the turbine efficiency. So this is the good news, right? We start rolling everything up now because we already found Y. So that was good, right? Now we found H8, which means that we can use this expression to find Y prime. We'd have to do a little bit of arithmetic. I'd get the Y prime, right? So I'd have Y prime times, I'd move this to the other side. This is minus, so this would be H8 minus H5 is equal to the stuff without Y prime in it, 1 minus Y times H8 plus Y times H13 minus H9, right? So I divide both of these things, right? So I take this out and divide this by H8 minus H5. So that would give me Y prime. That's good, because then as I went into this expression for the mass flow rate, right, now I have found H7 and H8. I had Y before, right? Now I know Y prime. So there's a lot of opportunity for me to screw something up, putting it into my calculator here, right? So take a bunch of lines if you can on your exam so that you don't look back and say like, oh, I wish I just wouldn't have fat fingered my calculator here, right? Check that your pump numbers, right? These last two numbers are pumps, that those ones are negative and these 3 turbine numbers are positive, or 4 turbine numbers are positive, but this will give me my mass flow rate, right? And then I can put all of that into this monstrosity of an equation over here, and I can get my thermal efficiency. Right? And on an exam, you know, this is probably more like the type of state table that you'd see on an exam. Not an empty state table, but a state table that's mostly filled. This would not be a bad exam problem. Although, you know, it obviously took a long time. I might not ask you all of these things, but you know, if you get a big monster kind of cycle like this, the state table will be something like this, where you have some things to fill out. So you get to demonstrate your understanding that you know how to do an ideal pump. That's something that people often get wrong. So maybe I would ask you to do that. You could on the final also see some kind of a second law type problem. You know, demonstrate to me that for example, the condenser, maybe, or the open feed water heater, that one of these things, find the entropy generation rate or something? Right? That's the kind of thing that you could ask, that you could get asked. So I think that was a good question. Does anybody have questions, comments about this solution, or just other things about the exam? Or does anybody want to volunteer to bring in a diesel problem or an Ottawa cycle problem tomorrow? Okay, if not, so somebody can bring a problem tomorrow. If you do,